nature of electronic transitions and the factors affecting it. After studying this module, you shall be able to learn about the important terminologies in UV visible spectroscopy, differentiate between the factors causing the change in the UV visible spectrum, understanding of the effect of conjugation on the position and intensity of UV visible bonds, analyze the effect of solvent on electronic transitions, know about the effect of pH on the UV visible absorption bands. Now starting off, we would like to begin with the introduction of the same. Ultraviolet visible spectroscopy involves the absorption of ultraviolet visible light by a molecule, causing the promotion of an electron from a ground electronic state to an excited electronic state. Although there are 6 possible transitions, namely the transitions being sigma to sigma star, pi to pi star, n to pi star, sigma to pi star, pi to sigma star and n to sigma star. The most commonly observed transitions in organic molecules are pi to pi star, n to sigma star and n to pi star. The n to pi star, that is the R band transitions, usually lie in the UV visible region, whereas the transitions such as sigma to sigma star and pi to pi star, which constitutes the K band, as well as the n to sigma star, lie in the vacuum or the far UV region. The lowest energy transition is typically that of an electron in the highest occupied molecular orbital, also denoted as HOMO, to the lowest unoccupied molecular orbital, also denoted as the LUMO. Electronic transitions may be intense or weak according to the magnitude of Emax that corresponds to allowed or forbidden transitions as governed by the selection rules of electronic transitions, which states that the transitions accompanied with a change in spin states are not allowed. Thus, S to S, that is singlet to singlet, triplet to triplet are allowed because of similar spin states, but singlet to triplet and triplet to singlet are forbidden due to change in the spin states. S here stands for singlet and T here stands for triplet. Important terminologies in UV visible spectroscopy. We now come across various important terms which are used in the spectroscopy, like first the chromophore. When a molecule absorbs electromagnetic radiations in the ultraviolet visible range, a transition between different electronic energy levels occur. The wavelength of absorption is a measure of separation of energy levels of the orbitals concerned. Now, the nucleus holding the electrons together in a bond determines the wavelength of radiation to be absorbed because of the strength by which the nucleus is holding on to the electrons. Thus, the nuclei with which the concerned electrons are bound affect the energy between the ground and the excited states. Therefore, we can say that the energy of transition and the wavelength of radiation absorbed are properties of atoms, not the electrons themselves. The group of atoms due to which absorption occurs is known as a chromophore. Now, telling a very specific definition of chromophore. A chromophore can be defined as an isolated covalently bonded group that shows a characteristic absorption in the UV visible region. For example, C double bond C, C double bond O, C double bond N, N double bond N R, NO2, etc. type of covalently bonded groups. If a compound absorbs light in the visible region, that is ranging from 400 nanometer to 800 nanometer, only then it appears colored to our eyes. Therefore, a chromophore may or may not impart color to a particular compound depending on whether the chromophore absorbs radiation in the visible or in the UV region. There are no standard criteria for the identification of a chromophore simply because the wavelength and intensity of absorption depend on many factors such as the molecular environment of the chromophore and the solvent in which the sample is being dissolved. Now, other parameters such as the pH, the temperature also may cause changes in both the intensity and the wavelength of the absorption maxima. Now, all the compounds having the same functional group will tend to absorb at the same wavelength, and the other factors such as conjugation and substituents if they are absent. Now, the next important term in UV visible spectroscopy is an auxochrome. Now, what is an auxochrome? The substituents covalently attached to a chromophore which themselves do not absorb ultraviolet or visible radiation, but their presence changes both the intensity as well as the wavelength of absorption, are known as auxochromes. The substituents like methyl, hydroxyl, alkoxy, halogen, amino group, etc. are some examples of auxochromes. Now, they are also called color enhancing group because, as it has been already discussed, they are enhancers to the chromophore. The actual auxochrome groups like CH3, ethyl group and the halogen like chlorine have very little effect, usually a small red shift of 5 to 10 nanometer. Other groups such as NH2, that is the amino group, and the NO2 like the nitro group have a strong effect and completely alter the spectra. Auxochrome generally increases the value of absorption maxima. The extended conjugation brings the lowest excited state, the LUMO, closer to the highest ground state, that is HOMO, as has been already stated before, and thus permits a lower energy, longer wavelength transition. Actually, the combination of chromophore and auxochrome behaves like a new chromophore having different value of absorption maxima. Now, for example, as you can see, the benzene here shows lambda max at 256 nanometer, whereas aniline shows lambda max at 280 nanometer. So, the addition of NH2 group has increased the lambda max value. Hence, the NH2 group acts as an auxochrome and causes the shifting of lambda max to a greater value. Now, coming on to the bathochromic shift or the red shift, as we know. The shift of an absorption maximum towards longer wavelengths or lower energy is called as bathochromic shift. It may be produced due to presence of an auxochrome or change in solvent polarity. Now, because the red color has a longer wavelength than the other colors in the visible spectrum, therefore, this effect is also termed as the red shift. Coming on to the hypochromic shift or the blue shift, the shift of an absorption maximum towards the shorter wavelength or the higher energy is called hypochromic shift. It may be caused due to the presence of an auxochrome or change in solvent polarity again. Now, because the blue color has a lower wavelength than the other colors in the visible spectrum, hence this effect may also be termed as the blue shift. This is clearly depicted in the figure shown. Coming on to the third type of effect, which is known as the hyperchromic effect. It is an effect which results in increased absorption intensity. The introduction of an auxochrome usually causes hyperchromic effect. Now, for example, consider benzene, which shows the B band, which is the secondary band in UV visible spectra at 256 nanometer, as has been mentioned earlier, and having an Emax value of 200, whereas aniline shows the B band at 280 nanometer and with the Emax at 1430. Thus, you can notice the increase in Emax, students, due to the hyperchromic effect of auxochrome NH2 introduced in benzene. Coming on to the hypochromic effect. An effect that results in decreased absorption intensity is called hypochromic effect. Now, as I would like to tell you, this is caused by a group which distorts the geometry of the molecule. In case of hyperchromic effect, it was a group which increases the geometry or the stability of the molecule. Here it is caused by a group which distorts the geometry of the molecule. For example, biphenyl shows a lambda max at 250 nanometer with a Emax value of 19,000, whereas 2-methyl biphenyl absorbs at lambda max 237 nanometer with an Emax of 10,250. The decrease in the value of absorbance is due to hypochromic effect of the methyl group, which distorts the chromophore by forcing the rings out of coplanarity, resulting in the loss of conjugation and hence a decrease in lambda max. This is clearly shown in the figure, as you can see. The hyperchromic and the hypochromic effect can be explained by taking the example of a biological molecule that we are all aware of, that is DNA. DNA absorbs in the ultraviolet region of the spectrum due to the conjugated double bond and ring systems of purine and pyrimidine bases. Now, the absorption of single strand DNA is higher than the absorption of double strand DNA. Now, we would like to discuss why this phenomena takes place. The two strands of DNA are bound together mainly by the stacking interactions, hydrogen bonds and hydrophobic interactions between the complementary bases. The hydrogen bond between the paired bases in the double helix limits the resonance of the aromatic ring of the bases, which results in decrease in the UV absorption of the double stranded DNA. Now, this can be termed as hypochromic effect of the double stranded DNA. When the DNA double helix is separated into its two fragments, the interaction forces holding the double helical structure, as has already been discussed, gets disrupted, that is the stacking forces, the hydrogen forces. As a result, intensity of absorption maxima increases, that is, we notice a hyperchromic effect as the bases are now in a free state and do not form hydrogen bonds with complementary bases. So, students, putting your attention to these effects in double stranded DNA, generally the absorbance for single stranded DNA is 37% higher than that for double stranded DNA at the same concentration. I hope now you can appreciate the difference between hyperchromic and hypochromic effect. Next, we move on to factors affecting the position of UV visible bands. First of all, I would like to discuss with you effects of conjugation. Now, when two or more chromophores are conjugated, the absorption maxima is shifted to a larger wavelength or a shorter frequency. Conjugation increases the energy of HOMO, that is highest occupied molecular orbital, and decreases the energy of LUMO, that is the lowest unoccupied molecular orbital. Now, as a result, less energy is required for an electronic transition in a conjugated system than in a non-conjugated system. This has been clearly and finely depicted in figure. Now, the next figure, it clearly shows that the number of conjugated double bonds increases the value of lambda max to a higher value. Now, the more the number of conjugated double bonds there are in a compound, the less energy is required for an electronic transition. As we have discussed earlier, the facts about HOMO and LUMO, the transitions energies being lowered, and therefore the longer is the wavelength at which the electronic transition occurs. Now, it is noteworthy here that the conjugation of two chromophore not only increases the lambda, but also increases the intensity, or we can say the molar absorptivity. This effect of conjugation can be shown by the spectra of polyenes, which can be depicted by the general formula CH3, CH double bond CH, N, where N is 3, 4 or 5, then again CH3. Now, considering the case of simple alkene, that is ethylene, we have only two molecular orbitals. One is the ground state pi bonding orbital and the other is excited state pi star anti-bonding orbital. Now, but in the case of conjugated dienes, the pi molecular orbital of the two separate C double bond C groups combine to form two new bonding molecular orbitals, which can be designated as psi1 and psi2, and two new anti-bonding molecular orbitals designated as psi3 star and psi4 star, as can be depicted in the figure clearly. Now, it is clear that the transition of lowest energy, that is pi to pi star transition in conjugated systems, is psi2, which corresponds to the HOMO, to psi4 star, which corresponds to LUMO. Hence, we can say that the conjugated dienes absorb at relatively longer wavelengths or lower energy than do the isolated alkenes. Now, students, I would like to attract your attention towards the next fact, that is, as the number of conjugated double bonds is increased, the gap between the highest occupied molecular orbital, which is the HOMO, and the LUMO, which is the lowest unoccupied molecular orbital, is progressively lowered. Therefore, the increase in size of the conjugated system gradually shifts the absorption maxima to longer wavelengths or lower energies. Now, if a compound has enough conjugated double bonds, it will absorb visible light and the compound will appear colored to our eyes. Consider beta carotene, which is a precursor of vitamin A. This beta carotene has 11 conjugated double bonds, as can be seen in the figure, and its absorption maxima gets shifted from ultraviolet to blue region of the visible spectrum, giving it an orange color. Now, in a similar fashion, the methyl group also produces a betachromic shift, or also called as the red shift. Although methyl group does not have pi electron or unshared pair of electrons, it is considered to interact with the pi system through its CH bonding orbitals, also known as and also taught as in the classes as hyperconjugation or sigma bond resonance. This can be further shown in the figure, the case of hyperconjugation. Similarly, in case of other conjugated chromophores, that is conjugation with the heteroatom, the energy difference between HOMO and LUMO is lowered, resulting in a betachromic shift or a red shift. Now, as has been discussed thoroughly above, carbonyl compounds show both pi to pi star, which is an intense and having shorter wavelength, intense transition with a shorter wavelength, and N to pi star, which is a less intense transition with a longer wavelength. The introduction of polar substituents on the alpha carbon of an aliphatic carbonyl do not affect the N to pi star transitions. But in the case of cyclic ketones, a betachromic shift is observed. Now, taking this case in detail, this effect is more when the auxochrome is at an axial position. The shift is almost 10 to 30 nanometer than that when it is present at an equatorial position. Now, equatorial position substituents will have a shift of 4 to 10 nanometers. Now, substitution on the carbonyl group by an auxochrome with a lone pair of electrons such as amide, acids, esters, acid chloride, etc. causes increase in the energy of pi star orbital, leaving the n orbital unaffected. As a result, N to pi star transition is shifted to a shorter wavelength called as the hypochromic shift. However, a little betachromic effect is observed on the transition pi to pi star. Such betachromic effects are caused by resonance interaction between carbonyl bond, that is a CO bond, and the lone pair on the heteroatom. If the carbonyl group is conjugated with a CC double bond, that is alpha beta unsaturated compounds, both pi to pi star and N to pi star transitions shift to a longer wavelength compared to the unconjugated carbonyl compounds. However, the energy of the N to pi star transitions does not decrease as rapidly as that of pi to pi star transitions. Now, if the conjugated chain becomes long enough, the N to pi star band is buried into the more intense pi to pi star band system. The molecular orbital of alpha beta unsaturated carbonyl system along with the isolated carbon-carbon double bond and a carbonyl group clearly. Now, taking into account the effect of steric hindrance on the UV visible spectrum. The UV spectroscopy is very sensitive to the distortion of the chromophores. We know that the position of absorption maximum and the intensity depend on the length and effectiveness of the conjugative system. Now, electronic conjugation works best when the molecule is planar in configuration. As you remember earlier from the earlier classes, the Huckel's rule. If the presence of an auxochrome prevents the molecule from being planar, then it may lead to the red or the blue shifts depending on the nature of distortion. Now taking an example and showing the same, the diene 1 which is shown is expected to show absorption maximum at 237 nanometer, the linear 1,3-butadiene, but the distortion of chromophore causes it to absorb at 220 nanometer. This blue shift is due to the loss of conjugation as the structure is not planar. Now similar trends can also be observed in compounds where geometrical isomerism is possible. It is found that generally the trans isomers show lambda max at a longer wavelength and Emax, that is the molar absorptivity or molar extinction coefficient, is higher than for the cis or the mixed isomer. For example, taking a look deeper into this fact, for example consider the trans stilbene which is shown at number 2 absorbs at longer wavelength and greater intensity, that is lambda max is equal to 295 nanometer and molar absorptivity at 27,000 than this cis stilbene which is just next to it, which shows the lambda max at 280 nanometer and molar absorptivity at 13,500 due to steric effects in the cis conformer as compared to the trans conformer. Now it is due to the more effective pi-pi orbital overlapping in the trans stilbene which results in achieving coplanarity of pi system more readily than in cis stilbene. In cis isomer, due to overcrowding or bulkiness of the groups on the same side of the double bond, planar geometry is distorted and hence you can see the difference in lambda max and molar absorptivity. Now moving on, taking another example such in cases of biphenyl and its 2-methyl and 2,2-dimethyl analogues. Biphenyl system is not completely planar, 2 rings being at an angle of 45 degrees, and in 2-methyl biphenyl the 2 rings are pushed even further out of coplanarity, resulting in a diminished pi-pi orbital overlap, which results obviously in blue shift because the coplanarity has been disturbed further and less intensity is also observed. The biphenyl numerically has a lambda max of 250 nanometer with a molar absorptivity of 19,000 and comparatively 2-methyl biphenyl as shown has a lambda max at 237 nanometer with a molar absorptivity of 10,250. I hope now you can appreciate the difference between the two structures and the coplanarity and its importance. Next we come on to the effect of solvent. The absorption spectrum depends on the solvent in which the absorbing system is dissolved. Now generally the choice of system which has already been discussed can shift peaks from shorter to longer wavelengths. Now this depends on the nature of the interaction of the particular solvent with the environment of the chromophore in the molecule under study. It is usually observed that ethanol solutions give absorption maxima at longer wavelength than hexane solutions. Water and alcohols can form hydrogen bonds which results in shifting of the bands of polar substances. Since polarities of the ground and excited state of a chromophore are different, hence a change in solvent polarity will stabilize the ground and excited states to different extent, causing change in the energy gap between these electronic states. Now highly pure non-polar solvents such as saturated hydrocarbons do not interact with solute molecules either in the ground or in the excited states, and thus the absorption spectrum of a compound in these solvents is similar to the one in the pure gaseous state. Moreover, polar solvents such as water, alcohols etc. may stabilize or destabilize the molecular orbitals of a molecule either in the ground state or in the excited state. Therefore, the spectrum of a compound in these solvents may significantly vary from one recorded in a hydrocarbon solvent. Now, considering the pi to pi star transition and the effect of solvent in these. In case of pi to pi star transitions, the excited states are more polar than the ground state. Now, if in case of polar solvents, the dipole-dipole interaction reduces the energy of the excited state more than that of the ground state. Thus, a polar solvent decreases the energy of pi to pi star transitions, and hence the absorption in a polar solvent such as ethanol will be at a longer wavelength, that is a red shift will be observed than in a non-polar solvent such as hexane. Considering the N to pi star transitions, in case of N to pi star transitions, the polar solvents form hydrogen bonds with the ground state of the polar molecules more readily than with the excited states. Consequently, the energy of the ground state is decreased, which further causes the increase in energy difference between the ground and the excited state energy levels. This is clearly shown in the figure. Therefore, absorption maximum resulting from the N to pi star transitions are shifted to shorter wavelength, that is a blue shift is observed with increasing solvent polarity. Now, this can be clearly seen with the no solvent interaction and the polar solvent interaction with the energy level diagram shown here. Now, next comes the effect of sample pH on the UV visibles. The pH of a sample solution can also have a significant effect on the absorption spectra. How? The absorption spectra of a certain aromatic compounds such as phenols and anilines change on changing the pH of the solution. Now, let us understand how this phenomena works. Phenols and substituted phenols are acidic and display sudden changes in their absorption maxima upon addition of a base. After the removal of phenolic proton, we get a phenoxide ion. In the phenoxide ion, lone pairs on the oxygen are delocalized over the entire pi system of the aromatic ring, and this increases the conjugation of the same. Extended conjugation provided by the phenoxide ion leads to a decrease in the energy difference between the HOMO and the LUMO orbital, which thus results in a red or a betachromic shift to a longer wavelength and a lower energy, along with the increase in intensity of absorption. Now, moving on, this phenomena of resonance in the phenoxide ion is clearly shown in the figure. Similarly, an aromatic amine gets protonated in an acidic medium, that is the pH is lowered, which disrupts the conjugation between the lone pair on the nitrogen atom and the aromatic pi system. Now, what happens after the disruption of that lone pair? This results in the blue shift or the hypochromic shift to a shorter wavelength and a higher energy, and thus we also observe a decrease in intensity. This is clearly shown by the protonation of the aniline leading to the formation of anilinium ion. The acid base indicators are another example, a fine example how the pH of the solvent affects the UV visible spectrum. Now, as we know, the acid base indicators, that is the pH indicators generally which we use in the titrations in the laboratories, have their applications due to their absorptions in the visible region of the UV visible spectrum. A small change in the chemical structure of the indicator molecule can cause a change in the chromophore, which absorbs at different lambda max value in the visible spectrum, resulting in significant color change at different pH values. Now, one such fine example is that of a well-known indicator such as phenolphthalein. Now, let us take this example in detail. Phenolphthalein is a weak acid which dissociates in water to give the anion, which results in extension of the negative charge of oxygen atom and leads to a substantial bathochromic shift to a longer wavelength and a lower energy. Thus, the anion of phenolphthalein is orange colored while its non-ionized form is colorless. This forms the basis of many titrations. At acidic and neutral pH, the equilibrium shifts to the left and the concentration of the anions is too low to observe the pink color. However, under basic conditions, the equilibrium shifts to the right hand side and the concentration of the anion increases and we observe a pink color which marks the endpoint of a titration sometime. Now, this is clearly shown in the figure, the change in the pH and the effect on the structure and thus the effect on the UV visible spectrum. Therefore, the UV visible spectra of such compounds should be regarded in a suitable buffer solution to maintain the pH at a constant value. The buffer though needs to be transparent over the wavelength range of the measurements. If the buffer absorbs radiation, absorbance readings may be higher than the actual value observed. Students, now I would like to bring your attention to the effect of temperature and sample concentration on the shape of UV visible absorption bands. Now, first is the effect of sample temperature on the UV visible bands. The effect of temperature is less pronounced, however, it cannot be ignored. However, simple thermal expansion of the solution may be sufficient to change the band intensity. Therefore, to get more accurate results, the spectrum needs to take place at a specified constant temperature. The following three criteria, as I am going to state, may be given as a general effect of temperature on solution phase spectra. First being the band sharpness, which increases with the decreasing temperature. The position of absorption maximum does not move or moves very little towards the longer wavelength side with decreasing temperature. The total absorption intensity is approximately independent of the temperature. This can be well understood with the figure that has been shown at 20 degrees and minus 195 degrees Celsius. Now, moving on, we know that the vibrational and rotational states depend on the temperature. As the temperature gets decreased, the vibrational and rotational energy states of the molecules shall also be lowered. When the absorption of light occurs at lower temperatures, smaller distribution of excited state results, which then produces fine absorption bands than that at higher temperature. Now, it is seen that the position of the band maxima do not shift very much with decreasing temperature, but tend to move very little towards the longer wavelength, that is the red side of the spectrum. Now, next comes the effect of sample concentration. Now, we have studied Lambert-Beer law and the Lambert's law. Now, according to the Lambert-Beer law, it might be expected that the sample concentration is directly proportional to the intensity of absorption. But as you increase the concentration of the solute, molecular interactions can take place, causing changes in the position and shape of the absorption bands. Such effects need to be identified and taken into consideration for quantitative work. Now, the solvent used also affects the fineness of absorption band in UV spectrum. It has been observed that the polar solvents give rise to broader bands. Non-polar solvents show more resolution, while completely removing the solvent gives the best resolution. This is due to solvent-solute interactions. Now, if the dielectric constant of a solvent is high, there will be a strong solute-solvent interaction. For example, a polar solvent like water or ethanol has this ability of hydrogen bonding with the solute if the solute has a hydrogen bonding component, or simply through induced dipole-dipole interactions. The non-polar solvents can also interact through polarizability via London interactions, but the effect is very less. Depending on the interaction, this can cause the ground state and the excited state of a solute to increase or decrease. thus changing the frequency of the absorbed photon. Due to this very reason, there are many different transition energies that overlap in the spectra and cause broadening of the UV band. Now students, as we end this module, I would like to summarize whatever we have studied and whatever we have come across in this module. Number 1, we studied the chromophore as a functional group which is responsible for the absorption in the UV visible region. Next we studied the auxochrome. Auxochrome is a molecule which does not absorb itself but increases the value of absorption maxima when covalently attached to a chromophore. The next is shifting of the absorption maxima towards longer wavelength, which is known as the red shift, whereas towards the shorter wavelength is known as the blue shift. Now next was the hypochromic effect, which is the decrease of absorption intensity and increase in absorption intensity is called as hyperchromic effect. By extending conjugation, the wavelength of absorption is shifted to a higher value. This is what we have learned after studying of the effects. Next we learnt the position and intensity is greatly affected by the polarity of the solvent. We then came across the factors of temperature, concentration and pH of the solution sample, and they affect the position and position of UV visible absorption bands. Now recording the spectra at a low temperature gives rise to sharp absorption bands, whereas high temperature causes the broadening of UV bands. Next and the final, we came across the change in pH of the sample solution changes the value of absorption maxima either to a higher or a lower value.